Hi everybody, welcome to the second video in this series on inverse theory. So today we're going to cover linear inverse theory as well as regularization as well. So we've got a couple of data sets to look at. One of them is the height and the weight of Olympic athletes, and the other one is to do with Moore's law. We'll come on to that later in the second part of this video. The first part, we're going to cover some of the background theory that you'll need to be able to understand and implement your own solutions. Then when we go on to the second part, we're going to code in Python from scratch the fitting of various functions to these data sets. So I hope you find it interesting. Let's crack on with the theory.
So we're going to start off with a very simple equation here. Y equals ax plus b is the equation of a straight line. But you can see that there are subscripts on the y and the x. This is because this is the value of the individual data point. So I will range from 1 to n being the number of data points. You have, like in the graph you can see here, you're going to have a multitude of different y and x values. So what we can do is we can stack all of these y and x values on top of one another and essentially have a whole bunch of simultaneous equations to solve for a and b. Now what we're going to do is, instead of having simultaneous equations, we're going to show this in a vector format. So here's the vector format. It's very simple. All we're saying here is that the vector of y values should be equal to the gradient times the vector of x values plus the intercept. The caveat here is that we're assuming that there is absolutely no noise in the model. And we know that real life is not like that, so any measured data would probably have measurement error but also systematic error associated with it, and we're not including that here. So there should be an additive noise term, but it's not included. Now this is for a straight line. What if we wanted to fit something other than a straight line? What if we wanted to fit a quadratic, for instance? Well, we could easily just add an extra vector onto there, which corresponds to the square of the x values, and have some other coefficient that we need to fit as well, as we can see here. So we've got a couple of values now that we want to find. We've got gamma, we've got a, and we've got b. So these are some coefficients that we need to find. So what I'd like to do is I'd like to separate them from the data. So that's the things that we want to find, and then the x values and the y values of the data that we have. So it'd be nice to separate them off. So that's what I'm going to do now. I'm going to have a vector of just my model parameters, gamma, a, and b, and a matrix of all of that other information, so the x squared, the x's, and then I'm also going to put a vector of ones there as well. So we can think that actually the b value is multiplied by x to the 0, which is of course 1. So now we've got our matrix vector version of the equation we just had, and if you want to verify this for yourself, you can do the matrix vector multiplication on the right. Now what I'm going to do from now on is actually use variables for these vectors and matrices rather than writing the whole things out. So typically you would have the observables represented by d, so that would be the vector of y values in this case. The matrix would generally be a capital G, and the model parameters would be m. And this is a typical setup you've seen a lot of literature, but for my purposes here, we're going to represent the vector of y's as a capital Y. So here we have our equation where we've got our vector of observables y, and that's equal to our matrix G, which is sometimes called the data kernel, and our vector of model parameters that we want to estimate m. So the trick here is that we want to rearrange this equation for m only. So we're going to do that in two ways. We're going to first just directly rearrange this equation, but then we're also going to pose it as a cost function and then solve that cost function through least squares method. So the first thing we want to do with this equation, if we're going to rearrange it, is we want to move the data kernel G onto the left hand side of this equation. So if G was square, that would be easy. We could directly invert this matrix. But if it isn't, then we need to make that matrix square. So the way to do this is to multiply both sides of this equation with the transpose of G. So now this matrix product G transpose G is square, so we can invert it. So to get rid of G transpose G from the right hand side of this equation, we just need to multiply by the inverse of G transpose G on the left. So we do that, and we have our model vector on its own and an equation to solve that model vector given only the data kernel and the vector of observables y. So one caveat to this is that G transpose G must have an inverse. If it doesn't have an inverse, we can't multiply on the left by that said inverse. And I'm not going to go through all the conditions which must be met for a matrix to be invertible. I'm just going to link to a Wolfram website that lists all of those conditions. So now we're going to go back and try and solve that original y equals gm, that original line fitting problem in a least squares sense. So what we're first going to do is we're going to move the matrix vector product of gm onto the left hand side of the equation. So now what we have is y minus gm equals 0. What this is saying is that the difference between the vector of observables y and the matrix vector product of the data kernel g with our ideal model parameters m should be a vector of zeros, but we don't want the output to be a vector. We really want it to be a singular value that we can use as a metric of how well our fit is. We know it's not going to be 0 because most data has noise with it, but at least we want that to be as small as possible. So this is where the least squares aspect comes in. We're going to apply an L2 norm here, which is to say we're going to have the L2 norm of y minus gm. Now an L2 norm of a vector simply is the sum of the squares of the individual values of that vector. So when we're saying that we want the L2 norm to be close to 0, what we're saying is that we want the difference between our observables and our modelled y values, represented by the matrix vector product of the data kernel G with our model parameters m, to be as small as possible. So we're going to call this L2 norm of the residuals a cost function, and we'll come back to this and add to it later on in this episode itself. So how do we find the minimum of this cost function? Well, if we assume that this cost function, as a function of the model parameters, is itself convex, then we can find the derivative with respect to the model parameters and find when that equals 0, and then that will be a global minimum. So I've outlined here what is the derivative of that cost function with respect to the model parameters, and I'm not going to go through the derivation, but it's basically an application of the chain rule. And as you can see, the form of it is actually quite similar to what we've seen before. If we divide both sides by 2 and then we multiply out these brackets, we'll get a very similar equation to what we've seen before. So to find the model parameters m, all we have to do is move g transpose y onto the right hand side of the equation and then multiply both sides by the inverse of g transpose g. So we're almost there. I just want to cover one more thing, and that is regularization. So if we want to apply some a priori assumptions about the model, we can do this in the form of regularization. So for instance, if we expect the model parameters to be small, or we want them to be small, we want to enforce that constraint, we can add that to that cost function we saw. So if we want them to be small and we still want the cost to be small, then all we have to do is add an L2 norm for the model parameters. This will ensure that they remain small, because if they are large, then the cost becomes large, and that is something that we're trying to minimize. So the lambda term here is basically the strength of the regularization we want to apply. If lambda is large, then the model weighting becomes much more important. If lambda is 0, then we're essentially applying no weighting to the model parameters at all. So the derivative of this cost function with respect to the model parameters is very similar to what we've seen before. The only difference is we have this additive term of the coefficient of regularization lambda multiplied by the model parameters. So when we rearrange this equation, we're going to apply a little trick by saying that the lambda m term is actually lambda times the identity matrix I multiplied by m. So then when we take the common m term out, we're left with, inside the brackets, g transpose g plus lambda times the identity matrix. So this is an example of wanting to weight the model parameters to be small. This is sometimes called Tikhonov regularization, but it's not the only regularization that we can apply. For instance, if we wanted the derivative of the model parameters to be small, i.e. we want them to not change very quickly from one model parameter to the next, then we can add regularization to do that. And here's an example of that, including the derivative. So here the capital D represents a first order finite difference derivative matrix. The last thing I'd like to cover before we get into the practical side of things is that sometimes when a function doesn't seem like it would fit in this framework, for instance fitting an exponential function, we can often linearize that. So for instance, if we took the natural log of those observables, those y values, then actually this problem becomes fitting a straight line, which we've already covered how to do.
So thanks for watching, hope you found that educational, and stick around and we're going to apply these methods to some real world data sets using Python and the NumPy package. So if you haven't already, like and subscribe, and we'll see you in the next video.